Hello, today I'm going to show you how to do a DIY capacitive water level sensor using ESP32 Touch Read function. In this project, we will cover the DIY capacitive sensor idea, which we will utilize the ESP32 Capacitive Touch Read sensor function to read and measure our homemade water level sensor. We will cover how to make the sensor, the overview of the ESP32 coding, and we will also cover how we calibrate the sensor in order to convert the raw reading from ESP32 Touch Read to real-world water depth. So this is what you will need for this project. We will need a conductor for this, and I will use copper tapes. I tried aluminum foil, but it is really hard to solder the wire to the foil, so copper tape works much better. Next, we will need something to seal the copper and also act as dielectric to the copper. So I used 5mm laminate sheets. I found that the 0.5mm sheets provide stronger structure than the 0.3mm sheets. Last, we need a thermal laminator, and this is the one I have. Let's start with the laminate sheet that we have. I'm going to divide it in half, as it is easier to work with a half sheet than with a full sheet. Then we're going to make dots where we want to cut the holes. Draw the same dots on the bottom side as well. Then we want to cut the holes on the top layer of the laminate sheet. Cut the copper tape, and I found that 6-inch length works well. Next, you will want to peel off the copper strips and then paste them on the bottom layer of the laminate sheet. Now, after we have cut and pasted the copper strips, we're ready to laminate them. You will want to warm up your thermal laminator. Through the holes we cut that are located on the top sheet, pre-tin the copper tapes. Solder a wire to each copper tape. Next, we will apply hot glue to seal the holes on both sides. Make sure the glue seals the soldering joints. Cut the sensors that we have just made in pairs. Now let's connect our homemade sensors to ESP32. I will connect sensors to touchpad channel 0 and channel 3. We will need one electrode to connect to ground. Later you will see why we need a ground. We will use ESP32 IDF compiler for this project. We found an Arduino IDE issue with the touch read function. Let me show you. As you can see the code, it reads channel 0 and channel 3. Channels 1 and 2 are already being used on my ESP32. Now let's run the software and download to ESP32. Let's run Serial Plotter so we can see the signal waveform. As you can see, the ESP32 is reading our sensors, and when I touch the sensors, you can see the reading is changing. You can see spikes even though I did not touch any sensor. This is not good. And if you look at the reading, the touch read number range is only from 0 to 50. For ESP32 IDF, the output range would be around 600 to 700, even with no touching. So let's close Arduino IDE and start ESP32 IDF software. And since I don't need Arduino project anymore, I will delete it. And now we are switching to ESP32 IDF compiler. For IDE, I'm using Visual Studio Code with a remote SSH to connect to my Linux computer. You will note that compiling on my Linux computer is much faster, and you can get the code I wrote from the link in this video description. Or you can use the example of touch read that comes with ESP32 IDF. But the example will print out 10 channels of touch read, which means there will be too much information that will flood the screen. So I rewrote the code that is easy for me to choose which channels I will use. In this case, I will use channels 0 and 3. Let's switch the USB cable to connect from Windows to my Linux computer. Next, let's build the project and flash to the ESP32 board. As you can see, the reading number from ESP32 IDF has more range as compared to Arduino IDE. If I touch the sensor, you can see the reading changes. However, we need software to plot the touch read like Arduino Serial Plotter. To make sure we don't have any reading spikes issue like we saw when we ran the Arduino touch read code, I wrote the software to plot the graph using Visual Studio 2019. Now let's switch USB back to my Windows PC. Let's run the software that I wrote to plot the graph. I will call the software that I wrote Serial Plotter. The basic idea is copied from Arduino Serial Plotter. Now let's connect to COM port. As you can see, we are receiving the data from ESP32. If I click Start Plot, you can see the chart is being plotted. If I touch the sensor, you can see the sensor reading dropped in the chart. And if I touch channel 0 sensor, you can see the graph is responding as well. If we leave the sensor alone, let's see if we see any spike. So there is no spike like we saw when we used Arduino. That's why I recommended that we use ESP32 IDF unless you find a way to fix the reading range and spike issues on Arduino. Now it's time to test our sensor to see if we can sense when it is immersed into the water. Let's restart the graph and bring in a cup of water. As you can see, the sensor reading suddenly changes as soon as it touches the water. Now let's see what happens if the sensor is immersed deeper into the water. You can see that the reading is decreased as it is immersed deeper into the water. So yay, it works. Now let's repeat the process a couple of times to see the response. Success! It looks like our sensor is working. But if we use the sensor without the ground, will it work or not? Let's check channel 3, which is the blue line on the graph. When we immersed the sensor into the water, the reading dropped a bit. But the reading won't change as the sensor is immersed deeper into the water. Without the ground pad, the sensor can sense the presence of water, but not the depth of the water. Next, I will show how we calibrate the sensor. We will use a vase of water with a scale attached. The scale will be an indicator to tell us how deep the sensor is immersed in the water. We will do two sizes of sensors. One is the 0.25 inch width, and the other is the 0.5 width. We will compare the characteristics of the sensors with the different widths. We will need to use serial plotter to be able to read the raw output from ESP32. And we will need LibreOffice Calc or Excel for us to enter and analyze the data. I already created a table for us to enter the data for both 0.5 and 0.25 widths. So let's begin. First, let me remove the 0.25 sensor. To mitigate an error, I will repeat immersing the sensor 5 times at each depth so that it shows on the table. Now we will repeat the same calibration process on the 0.25-inch sensors. So let's go. I think we've lost a little bit of water, so I'll add some more. Based on the raw reading, it looks like we still have more room to go deeper with the 0.25-inch width. So I will add more depth levels to the table. So now, analyzing calibration data. Now I will show you how we analyze the calibration data. Our goal is to define the transfer function between raw sensor reading and the depth. Let's average the raw reading that we have repeated 5 times. Sometimes my hand may be shaking or my eyes have not accurately read the results, so averaging the data will reduce any errors. Let's plot the graph between average raw reading and the real depth to get an idea how it looks. We will plot XY scatter chart here. As you can see, the relationship between sensor reading and the depth is not linear. So how can we define the transfer function of the sensor reading to a calibrated depth? Let me show you how to use the trend line in the spreadsheet to tell us what model of function is suitable for our sensor calibration data. First, you will need to click on any point of the XY chart, then hit right-click and click Insert. As you can see, there are many types of regressions, such as linear, logarithmic, exponential, and power. If you look at our graph, you can tell it is very similar to power regression. So let's choose power. Also click the check Show Equation and show R-square. The R-square will be the number to tell us how good is the regression model that we chose. If the number is closer to 1, it means the model fits very well. Then click OK. As you can see, there will be a transfer function equation. You can use this to convert the raw reading from our sensor into the calibrated depth. Also, the R-square told us that the regression model is a very good fit, as the value of 0.97 is very close to 1. There is another way that I will use in my ESP code. To show you, I will avoid using the floating point calculation in my code. We calibrated quite a lot of data, so if we assume that the data between each depth is linear, then we can create a table and use interpolation to calculate the data. In order to avoid using floating point calculation, I will use the Q number. You can get information about the Q number from Google, so I won't go into too much detail. I learned this technique from when I was working with some TI microcontrollers. The code that I wrote in ESP32 needs a table of Q numbers of sensor read and depth. I will show you how to convert the average sensor reading and the depth into Q8 number. You will need to multiply the number with 2 power of 8, then round it to the integer number. Next, I will make a copy using the same formula for Q8 depth. So let's make a copy of the entire table and name it Q8 sensor read and Q8 depth. For the 0.25 width sensor, I already finished converting the table to Q8. Here is the ESP32 code that has the calibration table that we copied from our spreadsheet. You can see the Q8 reading from the sensor has been copied from the spreadsheet. Also, we copied the Q8 depth data from the spreadsheet as well. We also copied the calibration table for the 0.25 sensor. You will need to add 2 more lines of code here to enable the scaling of each sensor channel. Now let's build the code and download to ESP32 to see if our calibration works. If we immerse the sensor into the water, ESP32 should show us the reading in centimeter. Now everything is reading 0 because we haven't yet put our sensor into the water. Let's immerse one of our sensors into the water. I will try to push the sensor to a depth of around 1.0 centimeter. Because of the camera angle, you may see that the sensor is not exactly at 1.0. If I push deeper to around 3.0 and then to around 6.0 centimeter, and now let's go to 12 centimeter. Yay, our calibration seems to be working. The sensor is quite accurate, and I would say it's around 1 millimeter accurate. Not too bad for our homemade sensor. Now let's try 0.5 width sensor. Whoops, there was a water stain on the small sensor. You may have noticed that it was not reading 0. Yay again! The calibration for the 0.5 sensor is working as well. So summaries. The ESP32 Touch Read function can be used to read the water level. The relationship between touch read and the depth of the sensor is nonlinear. One factor of the sensor is the width of the electrode. The small width of the electrode provided more dynamic ranges compared to the larger width, and the larger width of the electrode has more sensitivity but shorter dynamic range. This is the example application I wrote. We can remotely connect to ESP32. And we can get the depth reading via the TCP/IP socket. I hope you like it. I would like to hear from you, so please leave comments or questions and I will try my best to answer your question if I can. Please also click like or subscribe to my channel. I'm hoping to see you on my next video. Bye-bye.